Welcome to the use of GOES RSO imagery with other remote sensor data for diagnosing severe weather across the continental United States. This session was put together by Dan Bykos, John Weaver, Dan Lindsay, and Jim Purdom here at CIRA, and contributors are listed from other agencies down here at the bottom. The objectives of this session are to review the principles of using RSO imagery, the things we learned in mesoscale analysis, including identifying different air masses and such. But this time we're going to add a little bit more complexity to the details of mesoscale air masses, as well as we're going to begin to learn to analyze storm scale features. We're going to demonstrate during this session how RSO imagery can be used effectively with other data sets, and we will be presenting a number of advanced case studies from various CWAs across the continental United States. This image harkens back to what we covered in mesoscale analysis, RSO2. It's an example of identification of various air masses. Note the cloud streaks in the unstable boundary layer in the warm sector here, where the clouds are aligned basically with the surface flow. We'll also be talking about stable regions, as we did in mesoscale analysis, RSO, and boundaries separating various air masses, such as this warm front, which has been reinforced by a mesoscale convective complex overnight. There's a little stable air mass here, and this will be kind of our jumping off point to the more advanced material as we go along. One of the new things we'll be covering in this session is a great deal of information about storm structure. This is a conceptual model of a 0.5 degree tilt WSR88D reflectivity, PPI, of a supercell thunderstorm. This is the reflectivity here. I've also added to the diagram some of the storm scale features we're seeing, such as storm stationary outflow on the leading edge of the supercell and some trailing outflow here along the southwest flank, where a little bit of a flanking line may build up. Indicated in green here is a rear flank downdraft that results when mid-level drier, cooler air subsides and gets mixed into the mesocyclone. This is a schematic of the visible satellite imagery corresponding to that same supercell thunderstorm, showing a number of external cloud features, some of which we've talked about in the past, including the overshooting top, the above anvil cirrus, this real crisp anvil edge that's often associated with very strong thunderstorm updrafts. Sometimes we even find some little wave clouds along the edge of the anvil here indicating turbulence. Notice down here on the southwestern flank we show a flanking line. We've talked about that in the past. Some of the information we're going to be adding are features that develop in the outflow and inflow regions of strong supercells, including these lines of towering cumulus that often develop above an invigorated rear flank downdraft. They may or may not be attached to the storm. In some cases you'll see these lines of towering cumulus form in parallel lines along the leading edge of the invigorated RFD as it pushes out to the southwest. Another important feature, storm scale feature that we oftentimes see on satellite, are these inflow feeder towers here, feeder clouds, which form as compacted towering cumulus lines whenever the updraft of the supercell becomes very intense and directed. Here's an example of visible imagery showing some of those features. We've got this is from Heston, Kansas, 13 March 1990. We've got the overshooting top here, a pretty good thunderstorm anvil right in there. We've got good flanking lines showing in this region. We've also got some towers that are forming on the western edge of an invigorated RFD. We know that was an invigorated RFD because there were chasers on scene at the time that saw the back side of the towers kind of scoop out and dissipate as new outflow air started to push back toward the west. Up here in the inflow area we see these lines of compacted towers that we will be calling throughout this session the inflow feeder towers. Second example of this, to show that it happened in the past as well as now, is a thunderstorm top picture from the Wichita Falls tornadic storms of 10 April 1979. Again, a crisp anvil, overshooting top, some above anvil cirrus, a little bit of some cumulus back here as the RFD pushes out. There are big towers tacked onto the backside above the RFD in this case. And in this case, the anvil is so large that we can barely see the southern edge of these inflow feeder towers, but nonetheless they're there. Final example here, we've got the Plainfield, Illinois tornado case. Prior to this picture, about a half an hour prior to this picture, these inflow feeder towers were not here. The storm was producing a very strong derecho. We had signs of very strong outflow on the backside and a pretty good flanking line, but suddenly these inflow feeder towers appeared, and it was near that time that the storm transitioned from a strong microburst derecho producing severe thunderstorm into a tornadic thunderstorm and an F5 tornado touchdown near and in Plainfield.
Remember, when GOES RSO is in effect, it covers the CONUS, and all GOES imager channels are available. Now, when SBC issues a Day 1 enhanced risk or greater, GOES East will automatically be triggered into RSO mode. Similar story for Hurricane Watch or Warning. TPC will auto-trigger on an RSO. And remember, you can call RSO for any reason, not just severe storms. So when you're interested in rapid scan operations, imagery, remember to call your region focal point for RSO, and they're listed here.
Remember why RSO is important. First, we're able to capture atmospheric phenomena that occur on timescales less than 15 minutes, and that pretty much includes all mesoscale events. We do want to try to get a closer match to radar and lightning data sets, and remember, this is a very important point right here, we receive imagery much more quickly. The design specs for AWIPS call for standard satellite imagery to be delivered onto your AWIPS no later than 25 minutes after the image start time. For RSO, the design specs say 8 minutes. If you should ever run into a time when you don't get the RSO imagery within 8 minutes of image start scan time, please let us know, and we'll talk to somebody about that. Beyond that, remember, for any kind of weather event that involves the mesoscale in any way, it's better to have more is better than less, and quicker is better than slower.
Our first case is from 5 August of 2000, and for this case, we'll pretend like we're forecasting for Sioux Falls, Des Moines, and Omaha. The first thing we'll look at is the 10.7 micron IR imagery here during the overnight hours through the midday hours. And the first thing that catches your attention here is this MCS, and that would bring up the question, what areas have been stabilized by that MCS, and will there be any MCS outflow boundaries? Where are they? Are they over our region of interest here? So the first thing that catches our eye is this MCS moves across Iowa, and if we look in the wake of that, we can see some boundaries here actually, especially the later half of this loop. Also, I want to catch your attention here to this MCS in North Dakota as it moves off to the northeast. If we stop the loop and then go a little bit later to right here, I want to point out an MCS outflow boundary from that. One in North Dakota, you can see an outflow boundary right there. And then a little bit later on, it moves south. So perhaps that will move towards our region of interest. We don't know yet. And if we look a little bit later on as well, in east central South Dakota, we see another boundary right there moving towards the south, and by that time it's just about right there. So we have a few boundaries around, and as we continue to look at the products, we'll analyze the areas that have been stabilized by that MCS as well. Next is the sounding from Omaha in the morning, and typical of early August, we have quite a bit of moisture around, and therefore forecast Cape pretty large, and by the afternoon with temperatures getting up around 90. However, also typical of early August is shear that is somewhat questionable. The mid and upper level flow is sufficient here for severe storms. However, if we look at the low levels, the low-level winds are quite weak. In fact, the lowest wind is only light and variable there. So for that reason, we see a 3-kilometer storm relative velocity value fairly low, only 118 here. So as we go through the day, we will continue to monitor those low-level winds and see if they do indeed increase in speed. If they do not, it looks like the tornado potential is low on this particular day. Now let's go to the ETA composite here between mid and low levels. What I have here is the MSLP in yellow, and then the 500 millibar heights in green, low-level wind barbs in yellow, and then 500 millibar winds in this cyan color here. So we can see pretty much zonal flow and a shortwave going through in the morning, a low in southeast South Dakota with a trough line extending back towards central Nebraska, something like this. Okay, let's go 6 hours later now, and here we're adding the Cape forecast from the ETA. It's shaded here. Here we can identify, at least roughly, the different air masses. Here's that low in southeast South Dakota, and then somewhere southeast of that, something like that. We'll fine-tune this as we go on here. We have that air that's been stabilized by the MCS northeast of that line. Then we have that trough line back here with drier air to the west of that, and therefore less Cape. And then in between the two, we have a lot more Cape in here in our warm sector. So this is our warm sector, pretty much southeast of the low. Here we'll march through the observations from the morning period through the midday period. And as I do so, keep your eyes on eastern Nebraska and western Iowa in the warm sector. Here I'll stop at 17Z. Again, the low is somewhere around southeast South Dakota with the boundary here left over by the MCS with the stable air over here. The trough line extending back in this direction with our warm sector in here. Drier air back in here. And also notice these observations right in here at Sioux City, Norfolk, light and variable winds. And that was one of the questions we had earlier when we were looking at the sounding there. Would those low-level winds increase in speed? And so far it looks like the answer is no. Therefore, the tornado potential seems to be quite low on this particular day. Now let's go to the visible loop, and this is from 14Z through 2045Z, so through the early afternoon hours. And here's that MCS moving off to the east towards Illinois and Wisconsin. But then we look behind that, and remember some of those boundaries we analyzed in the IR imagery earlier. Now we can actually see those with some daytime heating, those cumulus clouds moving towards the south in an arc line, something like this, approaching our warm sector. And whenever you see a low-level convergence boundary approaching the warm sector, that's obviously something to key on. Also, another thing to point out here is I want to call your attention to southwest Nebraska. We see some clouds developing right there. I'll go ahead and stop the loop to highlight those. These are the clouds I'm talking about right here. And whenever you have clouds approaching your CWA here, you're concerned about what height are they at. Are these low-level clouds or mid-level clouds that are approaching our CWA? So in the next slide, we'll analyze what the height of these clouds are. Here we use the cloud height algorithm and AWIPS to evaluate what height these clouds are at. And we put our cursor over these clouds here in southwest Nebraska that we just saw in the viz. And we see the brightness temperature of -9. And it comes up with 20,200 feet. So that's over here where the yellow circle is plotted here, 20,200 feet, right around 500 millibars. So these are mid-level clouds approaching our CWA, and therefore most likely associated with a shortwave that's approaching our CWA. So we have a shortwave approaching, and we have a low-level convergence boundary that's approaching the warm sector. So things appear to be coming together for convective initiation within the next 2 to 3 hours here. Next, I'll show profiler data from Neligh, Nebraska, which is in northeast Nebraska. Here's that profiler data from northeast Nebraska, and what this helps is to confirm that shortwave that's approaching our CWA, as we see the winds here at mid and upper levels increasing during the day. Also, an interesting note here is that the low-level winds are indeed still quite weak. They are behind the trough line here, as you can see, but still those low-level winds appear to be quite weak. So again, confirming that the tornado potential seems to be quite low on this particular day. Next product here is from the GO Sounder, and this is actually the CAPE product here. Now this is available in AWIPS, but it's at a somewhat coarser resolution. In other words, it's averaging over larger boxes. This is called the single field of view product because we're averaging over smaller boxes and therefore getting some more details here. And what we see in this loop here is we're able to, again, refine exactly where those boundaries are, looking at the where the higher CAPE area is in our warm sector, where that MCS boundary is over here in Iowa, and then that trough line through eastern Nebraska. And I'll go ahead and stop this at a particular time, let's say right here. And here's our warm sector, eastern Nebraska, western Iowa. There were a few clouds around, and you can see those indicated here with the gray. And one thing to point out here is very high CAPE values, very close to these clouds, values near 8,000 joules per kilogram. And the reason is because it's suffering from diffraction near clouds. Therefore, you get somewhat higher than realistic CAPE values whenever you're very close to clouds like that. So that's just a word of caution. But if we go away from those clouds, we will see some values that are more realistic here, around 5,000 or so joules per kilogram of CAPE. Remember, the dew points were very high, and it was forecast to get around 90, so pretty good CAPE values here. And again, we see that MCS boundary, the low, somewhere around there, and then that trough line in eastern Nebraska. Here we go to our visible imagery. On this particular day, John Weaver and myself called for super rapid scan operations since GOES 11 was in science test. So we were able to get 1 minute imagery for this particular day. And here's that low-level convergence boundary that we had been concerned about moving towards the southeast into our warm sector. And we can also see another boundary just south of that. It shows up a little better as afternoon heating ensues here. And we can see convective initiation occurring. Also note these mid-level clouds that we had been concerned about associated with the shortwave. A couple interesting things to note with that. If I stop the loop at this time right here, we can see some clouds underneath those mid-level clouds that are oriented more like that, southeast to northwest. And those are stable wave clouds, and whenever you see that, that means a couple different things. One, that we're in stable air, and we know that since we're in dry air behind the trough line. And also, we have fairly significant forcing associated with that as well. Now, I want you to notice the timing of the arrival of these mid-level clouds when they become juxtaposed over the low-level convergence boundary. And there seems to be a pretty good correlation here in terms of when these clouds arrive over those low-level convergence boundaries over here. So it appears the shortwave in conjunction with the low-level convergence boundaries were key in terms of initiating these storms here. Now let's go to the radar, and this is a composite of the reflectivity from the Omaha, Sioux Falls, and Des Moines radars locations. And what I'll do is just toggle on the NLDN cloud-to-ground lightning data. Now we can see that first storm initiating right here along that northern boundary we had seen on the visible loop. And then that soon dissipates, and we get another storm just south of that go up. It has quite a bit of lightning with it. It's a pretty big storm as well. And then near the end of that loop, we can see another storm go up just to the northeast right over here. And I'll go ahead and stop the loop and point out a couple interesting things here. One is that this particular storm right here had quite a bit of hail with it. There were a number of reports of hail diameter sizes greater than 2 inches in diameter. And in fact, at 23:45, which is just about this time right here, there was a report of 3-inch diameter hail from this storm. So pretty big hail from this storm. And a couple interesting notes here as well. If we look right here, we can see a lot of positive strikes pretty close to the core here. And we can see the signature continue here and become most pronounced right around that time, and this time right here. A lot of positive strikes near the core. That means we have a positive strike-dominated storm, and the consequence of that is that we definitely know we have a severe storm. Very good chance that we have a severe storm whenever we see a high percentage of positive very close to the core. Next, let's look at the half-degree base velocity from the Omaha radar. And remember, we had been concerned about the low-level winds, that they were quite weak, and therefore we were thinking low potential of tornadoes. And indeed, if you look at the velocity here, you do not see a good mesocyclone signature here. And in fact, there were no tornado reports, just hail reports. So knowledge of the near storm environment, as well as continuing to monitor here, and we see a number of hail reports, but no tornado reports on this particular day. Now let's go to the next sequence of visible satellite imagery here, and we can see some interesting things with this particular storm here. What I want to do is stop the loop and go early on. Let's look for some of those storm scale features that John had mentioned earlier in some of those schematics. Here's our flanking line, and we can see just east of that flanking line some of those inflow feeder clouds right here. West of the flanking line, we don't see the cumulus above the invigorated RFD, but another interesting observation here is we see some clouds emanating away from the storm. I'll go ahead and draw them in, something like that, southeast of the storm. Not the anvil. The anvil is right up here. And one of the questions we had here was, what level are these clouds at here? Is this low-level outflow racing out ahead of the storm? So again, we went to the cloud height product, and we found out the height of these clouds were at mid-levels here. And I'll go ahead and show that in the next slide here. Here's the cloud height algorithm giving us an indicator of about where these clouds are at. And we found that they're at 17,000 feet, these clouds in question here, which is right around 550 millibars. So this is not low-level outflow that's racing out ahead of the storm. It's actually mid-level clouds. Their cause is unknown. However, we think they may be associated with gravity waves associated with the individual updrafts, the overshooting tops that we see. There's actually another one that occurs a little bit later on in this loop. In other words, you see an overshooting top, and then a little bit later you see these mid-level clouds racing out ahead of the storm. Finally, let's go to the radar loop as these storms are dissipating. And again, I will overlay the NLDN cloud-to-ground lightning data. And here we can see a pretty good use of the lightning data in terms of answering the question, when will I need to stop issuing warnings on these storms here? Well, if we overlay the lightning data here, we see a pretty good correlation between when the flash count starts to go down considerably and when these storms start to weaken and finally dissipate. So again, another use here of the lightning data in terms of helping you in your warning decision-making process in terms of answering the question when to stop issuing those warnings. Let's summarize this particular case here. In the synoptic scale, we saw those mid-level alto-cumulus clouds associated with the approaching shortwave play a role in convective initiation as they became juxtaposed with the low-level convergence boundaries in the warm sector. On the mesoscale, we saw different air masses and boundaries. We also saw indicators of stable air over Nebraska underneath that approaching shortwave. On the storm scale, we saw feeder bands but no cumulus lines west of the flanking line. And we used cloud-to-ground lightning data as well to determine the PSD nature of the storms, as well as a decrease in the flash rate as a precursor to storm dissipation. Now we'll go to our next case study.
This next case is over the northeastern U.S. It involves the Pittsburgh State College and Binghamton, New York, CWAs. During this case, we're going to focus ourselves on different air masses, identifying different air masses in advance of severe weather. Maybe learn to think a little bit more deeply into the problem as we look at the near storm environment. Give a little background to the case. We'll look at the ADA MSLP and surface wind forecast for the 2nd of June, 1998. The analysis here, if we look closely, there's a deep surface low over northeastern Wisconsin and northern Lake Michigan, front stretching down here through Illinois, and if you look closely, you'll see hints of some little pressure perturbations ahead of the front, and that will cause a little trouble later in the form of prefrontal squall lines. If we go to the 6-hour forecast, which is 18Z, we find that that low is expected to move from northeastern Wisconsin over into eastern Michigan, and finally by the end of the period, the low is expected to move all the way over here into eastern Ontario, dragging the front with it. By the end of the day, we expect to find that front right in the dead center of Pennsylvania. Here's the 10.7 micron infrared satellite loop from around 1000 to about 1315 UTC. Feature of interest here is this early day activity. There's some showers, cloud cover early in the period, crossing at least the northern part of the area that we're interested in. The center of the vortex is actually by mid-morning is moving out of the Pittsburgh CWA. There's still a few showers here, confirmed by radar. We're not going to show that, but at this point, but a few showers up here in northeastern Pennsylvania and southern New York. So one of the things we're going to be looking at is, of course, to try to search out where that where the rain-cooled air is going to meet with the air that was not affected by the overnight rain, and see if we can identify some boundaries. And of course, we'll be looking for other differences in air masses as well. Here's the Eta, Cape, Helicity, and Bunkers right-moving storm vectors. At analysis time, we can see that even at 12Z, we've got some pretty good Cape in the area. If we go forward to 18Z, we can see that the Cape is increasing substantially. There's a good deal of helicity forecast, upwards of 200. And if we go to the end of the day here, as the front moves in, we see Cape values reaching 2,500 or so, and very large values of helicity. So it's a pretty good setup. It's a pretty vigorous front for this time of year in the Northeast, and some pretty good Cape building up again for this time of year. We'll look now at some visible imagery, a visible loop which runs from around 1330 UTC to around 1745. And when you're looking at a visible loop in advance of expected convection, what you want to do first, of course, is to try to learn what the imagery is showing us about the various air masses. Obviously, the area over southwestern Pennsylvania is more unstable than the air over eastern Pennsylvania. And let me stop the loop here and go forward a little bit to a time when we see that clearly. Notice over here in the Pittsburgh CWA, we've got some good cloud streak development indicating some pretty moist, unstable boundary layer air over here. This particular line of deeper convection right here is actually a little ridge line along some mountains, and I'll show that on the terrain in just a minute. Meanwhile, over here in eastern Pennsylvania, we see that we don't have any, the skies are pretty clear, and we don't have any low-level Q development as yet. Up here in northeastern Pennsylvania and southwestern New York, we still have the remnants of that overnight system. Okay, now we go forward a little bit in time with the loop, and we begin to see some development in southeastern Pennsylvania, and some streets developing here. And if you're working, say, the State College CWA, what you want to focus your attention on is the fact that you've got this destabilizing air mass down here in southeastern Pennsylvania that's marked by the developing cloud streets, versus this clear area up here in northeastern Pennsylvania that has just recently cleared of those light showers from the early morning activity, and we'll look for a boundary setting up separating those two. And as you watch the loop continue out to its end, you see that unstable air is now moving further north toward northeastern Pennsylvania. That's going to be a boundary later that's going to be important. Here's a couple of soundings. In green, we find the Sterling, Virginia sounding. In cyan is the Pittsburgh sounding. Both areas both east and west of the Appalachian Mountains are unstable, obviously. The low-level flow is pretty much parallel to the streets as expected, and the air mass is pretty moist. That's clear. Neither sounding has a real significant cap, but notice that the Pittsburgh in cyan shows a much weaker inversion, and that kind of explains, or partially explains, why the cumulus streets start to develop there first. This is a terrain map pretty much over the Pittsburgh CWA. Note the ridge lines that I was referring to earlier. These ridge lines oftentimes develop cumulus before the other areas do, and it's a pretty good giveaway that the low-level air mass is unstable. Low-level southwesterly flow has an upslope component on the west face of some of these ridges. Be sure to be aware of the topography in your CWA, because as we'll show later, topography plays a big role not only in the western U.S. but also anywhere in the country where you have any sort of mountains whatsoever. Now here's a visible loop from a little bit later in the day. It runs from 1845 to 2315 UTC. It covers most of the afternoon, and there's a lot to talk about on this loop, so I'm just going to stop it and we'll kind of walk through it. We noticed that thunderstorms kind of develop in early afternoon in eastern Ohio here. You also see some thunderstorms developing up here in Canada. Nothing over the lake, because the lake is, of course, cool at this time of year. Temperatures over the lake average around 50 degrees Fahrenheit or so around the early part of June. So you have pretty much some subsiding air there. The actual front at this time, by the way, I won't show the surface data, but let me just inform you that the front is actually back here, well to the west, and this is one of those prefrontal squall lines we're talking about. And as we go forward in time, notice that this first line of storms forms and begins moving toward our CWA, and as it does, what you want to do is look at the character of both of these storms as they travel along. There's this storm and this storm that's going to be traveling right into Pittsburgh's area, and you'll see that as we go along, the southernmost storm, as you would expect, turns out to be the strongest storm, and there's a lot of signs on satellite that it is. On radar, it did have the highest reflectivity, and it did have a good mesocyclone. It's one to the north, had a little less reflectivity and was a little, didn't have a well-organized in-storm circulation. But notice on satellite here, you've got a good crisp edge to the anvil, one of the signs of a strong storm that chasers look for oftentimes. And up here in the inflow area, you see these inflow feeder towers that we talked about earlier. As the storm progresses along, it moves into our CWA, and these inflow feeder towers get larger, the overshooting top gets larger, and of course this storm on the south does have access to the inflow air, which is coming in the direction indicated by these cloud streets, which are basically the show the integrated shear vector in the boundary layer. So let's go forward a little bit in time and see what happens here. Notice this boundary in eastern Pennsylvania as this unstable air moves north to replace the clear air in western New York. Got a pretty good storm coming along here now, and if that storm can latch onto that boundary, that's one you're going to want to pay attention to. Another thing to notice here is, notice now, this is the cold front. Let me erase some stuff. This is the cold front right here, so the front is very strong. This is one of those prefrontal squall lines. And the front is so strong, in fact, that at this particular time, storms are developing at this point on Lake Erie and actually increasing in intensity as it crosses the lake, which is a sign of a very, very strong frontal lift associated with that cold front. And notice that there's new storms forming here on the southern shore of Lake Erie. Now, as our first storms move out, we do indeed have a tornado produced in association with those storms just about this time. A little after that, it's an F1 tornado, and so this overshooting top and these inflow feeder clouds mark the storm that's the strongest, and indeed that's the storm that has the tornado. We'll show some radar data in a minute. But one of the things that you always want to think about is, even if you have some storms go through your area, remember what that near storm environment is like. We've still got southerly flow. We've still got cloud streets coming up into our CWA from the southwest, and notice these little outflow boundaries that are being left behind by those storms. So now not only are you going to have an unstable air mass, very unstable air mass, a lot of moisture, a lot of CAPE in the boundary layer, available CAPE in the boundary layer, but now you're also going to have an outflow boundary thrown into the mix as the storms associated with this cold front move into your CWA. So we've got storm 1 going through here, and you may go, boy, I'm glad that's over. But in fact, what happens is the second storm comes along and latches onto that outflow boundary and becomes the strongest of the two. Now let's backstep here a little bit and see what happens to this storm right up in here, this particular storm right up in here. does produce some very, very large hail at right around this time as it moves along that boundary. And it's also leaving a boundary behind itself, and there's a second storm coming along here. So again, just because one set of storms passes through your area, the front's not here yet. We've still got good unstable air feeding into these areas, so be aware of the near storm environment even as you go into the warning mode. Okay, we'll look now at some Pittsburgh 0.5 degree tilt reflectivity data from around 2100 to 01, which goes just a little beyond the time of that last loop, and I'll show you what was going on radar. We've got some surface data overlay to assure you that we've still got that good, strong, rich southerly flow coming into the area. And in fact, now we have a jump in the radar. This is unfortunate because right about here we've got this storm right here, and this is actually some very intense inflow into storm 1, which causes sort of a merger into a main complex right here. Move that. And we get this tornado at 2155. Let me go back to 2155. Oops, sorry. Get this tornado at 2155 right in here, and following that we have this merger, which is sort of destructive in that this particular storm gets its inflow blocked off, and the storm weakens somewhat as time passes on. It turns into kind of an HP configuration. Still a pretty good inflow notch going on here, but the storm turns into principally a hailer until we get up to about here, when the storm redevelops into a nice tornadic storm. Notice the outflow being left behind here that we talked about on the imagery. You can see that outflow when it's close enough to the radar. And here's this second storm coming in back to the west. And now as we cross the eastern edge of the Alleghenies and the storm reconfigures itself, we get up here to around 2300, and we do get a report of an F2 tornado in this vicinity as well. However, as we go through time, this second storm now latches on to that boundary, and by 01 has turned into let me erase this, has turned into a tornadic storm, which now produces an F2 tornado, an F4 tornado right about this time right here. So, again, you can see all these interactions from many different data sources. Let me animate this loop now. When you're watching the radar and you're seeing how the reflectivity and velocity patterns evolve, it's very, very handy to flip back over to the visible satellite loop and just see what lies ahead for these storms as they move through their environment. In this case, the clue that the second storm was going to be just as severe, or maybe more so than the first, was the fact that the cloud streets that we saw on the satellite are still in existence, and now we've got the inflow air interacting with this outflow boundary that was very, very clear on the visible. As we get into the late afternoon and then after dark, one of the channels that you might look at on the satellite imagery, if you're still trying to monitor the near storm environment, in this case we don't need to, but it's still instructive to look at it here. Let me stop the loop. Looking at the 3.9 micron imagery, remember that the 3.9 channel has the ability to discriminate between water clouds and ice clouds, and in this case we're looking at water clouds here in lighter grays and ice clouds in darker blacks in black, and darker grays in black, and the speckly areas here are actually noise because the 3.9 channel can't sense beyond a certain colder than a certain temperature, and it kind of turns into noise. But the resolution on the 3.9 channel is kind of what prevents its use as frequently as it should be used for these purposes. 4:2 resolution at the equator, and maybe say 6:4 resolution up at this latitude kind of prevents it from being a big help. But still, you can clearly see that you can clearly see and track these outflow boundaries at night using this channel. And you can also see, if you look carefully, you can see some of these low-level cloud streets here that are forming in eastern Pennsylvania. 0.9 channel in the future you should be able to use it pretty closely to the way you use visible now in terms of looking for those low-level cloud streaks and boundaries and such. So in conclusion, not very complicated. You can use the satellite imagery to get a better handle on your morning setup. Remember, we found those different air masses. Looked at the areas where the streets were setting up early. They were setting up in the most unstable region. We saw a couple of lines of storms develop, and the first line interact with the second line interact with the remnants of the first line. And on the storm scale, we could track outflow boundaries really well on visible and pretty well on the 3.9 channel, as well as on radar, while the boundary was close enough to the radar to be seen. The fact that the destabilizing air was moving northward in eastern Pennsylvania to replace that earlier rain-cooled air is important, because the difference between the two sets up kind of a baroclinic boundary. And when the last storm of the day latched onto that boundary up here in northeastern PA, we had a pretty good-sized tornado produced. It was basically an F3 tornado and did some significant damage up in this region. Okay, so now we're going to move back out. We're going to move out west. We're going to look at the Pocatello, Idaho CWA from the 28th of April, 2003. And this case is going to show how terrain can affect the evolving severe thunderstorm situation, and how a knowledge of the local terrain in combination with satellite imagery and other data can help us understand where the severe weather is most likely to be. This first loop here is a loop of water vapor imagery from 0945 through 1830 UTC on the 28th. And the features to notice, of course, one you can't miss: off the northwestern coast of California, we see a pretty intense closed low, good extratropical cyclone going there. Other features to notice there's a little shortwave that seems to be ejecting into a diffluent zone through northeastern Idaho here, and a second shortwave rotating through the system through western Nevada as we get toward the end of the loop, which again is at midday. So by midday there's another shortwave approaching here, but this particular, for the first shortwave, actually did produce some pretty cool rains up here in northeastern Idaho. This is the 10.7 micron IR window channel data from 12Z to 1845. We're zoomed in a little closer now to our CWA, and notice that this channel is looking closer to the surface. One of the things that allows us to see where you've got terrain is the terrain features themselves, since they're going to warm up more slowly than the peaks are going to warm up more slowly than the valleys. And here we see a number of ridges that cross most of the state of, or eastern two-thirds anyway, of eastern Nevada. So we can see the terrain, but also look closely toward the end of the loop. Let me stop the loop here as we go along. Let me show you the terrain. This is the terrain. This is the cooler terrain right here, these little lines. As we step forward, we begin to see some brighter tops, some brighter spots forming on that terrain. There's one right there. And as we go through time, there's more and more of them, and they begin to move. And what that is those are towering cumulus that are developing due to the high-level heat source, and they're developing and they're blowing off toward the north-northeast, which is a clue about the low-level wind field in this region as the shortwave approaches. Notice also through this loop, interesting, that the shortwave here isn't moving nearly as fast as the shortwave here, and that's because we've got pretty good flow, pretty good jet going through Utah toward the northeast, and then we've got this other flow backing into the extratropical cyclone, and this area here has very weak flow over our CWA. This is a brief look at the terrain over southern Idaho. Pretty interesting. These ridge lines in Nevada actually extend up into this area right here, into the southeast part of our CWA. There's tremendous terrain differences in this region. I find it pretty fascinating, even though we're in Colorado here. Got the Snake River Valley, which is down at elevations down below 3,000 feet in many cases. This area up here around Boise is around 3,000 feet. You get here to Pocatello, office, and they're up near to 5,000 feet. And when we get, by the way, the terrain heights are indicated up here in the upper left. When we get when we get to these little ridge lines in southeastern Idaho, we see some of them going up as high as 8,000 feet. And that's one of the things we're going to be focusing on, is what effect this terrain has in severe weather situations. This is the Boise 12Z sounding from the 28th. The red line represents the lifted parcel based on forecast temperature and dew point, and they did realize temperatures and dew points similar to that. It shows about 1,000 joules per kilogram of CAPE, especially in the modified sounding. The forecast LFC is around 820 millibars, and the height of the freezing level is around 760. But recall that the Pocatello CWA is at a higher elevation, and therefore cloud base is going to be a lot closer to the ground. Also, for those of you who have taken lightning met 1 and 2, notice that there's a relatively deep positive area in the layer that's colder than minus 10C. Here's minus 10C here. We've got a fairly extensive part of the updraft that's going to be above or colder than that minus 10C. So even though it's April in the mountains, we can still expect some lightning production because we've got a good deep layer for that grapple and those ice particles to collide and charge up the grapple negative and the crystals positive. These are the surface observations overlaid with RUC 0-hour forecast MSLP for 1400 through 1800, basically mid to late morning. And notice the broad pressure trough that extends from northern Utah to western Oregon as we go through this time here. Pretty nice trough. There's a high pressure up here in Montana associated with the colder air from that overnight activity. Temperatures are definitely colder in Montana and western Wyoming, where the shortwave is still affecting the region. To the southwest, skies are beginning to clear, and temperatures are warming into the 50s. Notice that there's northeasterly winds over Montana and southerly winds developing over Utah and central Nevada. So there's a potential of setting up a convergence zone somewhere in here. As this shortwave approaches, we'll get some intensifying southerly flow headed this shortwave, and we've got this northeasterly flow to the north. So we want to watch for some setup of some sort of a boundary. Okay, this is a visible satellite loop a little bit later, 1530 to 1845. We got one of the things to notice is, remember, we've got this southerly, south-southwesterly flow here, some southerly flow here, and remember the surface data showed some northerly flow and northeasterly flow in this region. So somewhere in this area we've got some convergence, probably broad scale at this point. But one of the ringers that kind of gets added in when you have terrain to worry about is you've got this ridge line in southeastern Idaho here, so we've got a nice high-level heat source, and we've already got cumulus developing by the end of this loop. Note the cirrus across Utah. This is where the jet is the strongest. Remember that we're in kind of a difluent zone, but this makes this region sort of in the exit region or the difluent area of the upper jet. And the short wave is very, very slow to move out. That's going to be another key player as we go along here. So look how fast this short wave is coming, and look how slowly that short wave is moving. This is the ADA 500 millibar heights, vorticity, and ice attacks. The ice attacks are shaded. At 12Z, notice the vort max associated with that lead short wave, and the second vorticity max back here. We've got this one moving out of the area, and this one kind of coming in. It's fairly ill-defined. Kind of hard to know where those short waves are. In fact, if you didn't have satellite, I believe in this case, it'd be very difficult to tell that this and this was connected over here, and that this was actually the leading edge of that short wave there. Probably could, but I think satellite makes things a lot easier in that particular respect. By 18Z, we can see that secondary shortwave approaching or traveling into western Nevada, bringing PVA over our area of interest. There's still good difluence areas in the left exit quadrant of the jet, and there's some southerly flow here and some southwesterly flow here. That pattern continues as we go through the day. Let's go to the last time here on the 500, and we see by the end of the day it's very difficult to identify that short wave and where the PVA is going to be kind of noisy. Remember that the vorticity is a combination of circulation and speed shears, and we're very near the jet here, so there's bound to be a little bit of spaghetti, and it's going to be a little harder to identify short waves. And again, one place to go to try to get information on that is the 6.7 micron water vapor imagery. I think everyone knows that. Okay, we were talking about how there was southerly flow in Nevada and also Utah, and how there was northerly flow in Montana and northeastern Idaho. Let's see what the ADA tells us about that situation as the day goes on. Here's the 0Z, the 12Z 0-hour forecast. We do see that northerly flow associated with that overnight rain, that exiting shortwave. Now we see by midday, we begin to see this southerly flow develop in Nevada and Utah, and the northeasterly flow kind of weakens up here in the northern part of Pocatello's CWA. And finally, by the end of the day, the ADA believes that we're going to be replaced entirely with southerly flow, and that the warm front will push all the way to the northeastern Idaho border, and the easterly flow will be contained to Montana. So we're going to see how that goes. So basically what we're looking at here is this is Mesonet data, combination of Mesonet data that's available, it is available to Pocatello in real time on their AWIPS, so it's nothing that you can't see or look at. This is surface obs for 21Z over southeastern Idaho, western Utah, western Wyoming, northern Utah. Notice that the northerly flow at 21Z, which is mid-afternoon, is continuing. There's cooler temperatures, some higher dew points throughout the Snake River Valley. It's kind of pushing all the way down into the Snake River Valley here, and remember those ridge lines here. The northerly flow may be pushing all the way up to those ridge lines simply because there's almost no terrain between these ridge lines, no rough terrain in between these ridge lines and these mountains to the north. So we've got some pretty good cool air flowing out across the Snake River Valley and starting to upslope against these ridge lines, and we've also got developing cumulus on the ridge lines. Remember back to the visible imagery. So things are beginning to point a little different from what the ADA was talking about earlier. By this time we should be seeing southerly flow throughout most of our CWA. We're not seeing that. We're seeing the northerly flow persisting in the northern part of the CWA. To accent that point, this is the ADAS analysis of surface wind, ice attacks, and wind barbs at 22Z, which is an hour later. Now we can clearly see that that there's a line of convergence that's set up very near those ridges in southeastern Idaho. So this looks like the area to pay attention to, the area of action. If there's going to be any severe convection, this is probably where it's going to occur. So now let's look at some visible imagery. This loop here is going to go from 1700 all the way through 2330. In other words, basically the whole afternoon. At 1700, at the beginning of the loop here, we see the shortwave is still stuck out there near Boise somewhere, the center of it anyway, and we've still got some residual cloud cover and actually some embedded showers up in this area. See that on radar. I'm not going to show that right now, but we do have some showers here. Second shortwave is now, as we go into the loop here a little deeper, the second shortwave is now beginning to trigger some deeper convection just ahead of itself in south central Idaho, and watch the storms as they move out into the Snake River Valley. They're actually going downslope, and they're getting into lower and lower terrain and into cooler and cooler air, and as they do, the edges of the anvils become much more fibrous, and chasers would say flaky anvils. Meanwhile, let me back up here a little bit. You notice this one storm that is now traveling along these preconditioned air mass on the northern edge of these ridge lines seems to look much stronger on satellite. It's got a much crisper anvil to it. Like that, move it. A much crisper anvil to it, and as we march along through time, you can see it's latched onto that convergence boundary that seems to have set up on the northern edge of those ridges. We can also see a little flanking line here poking out from the southwest edge of the storm. A couple of those inflow feeder towers indicating that it's got a very intense inflow region to it, and as time goes on, the storm continues to look strong. In fact, it is a right mover in the sense that it is moving to the right of the mean level winds. But this right mover is moving a little bit faster since it's able to access basically air that's that has broken the cap along a lot of these ridge lines. So it's just moving along, triggering off, sort of propagating along a preconditioned boundary there. Here's some radar data that we made. We overlaid the reflectivity data on top of some terrain data. What I want to do is show you how this particular right-moving storm changes character as it moves between ridges and valleys. Remember that each one of these ridge lines has some pretty deep convection that's built up on it with time. The satellite imagery shows clearly that this is the most conditioned air, and if you'll notice in the valleys here, there's a little less cloudiness that's built up on the satellite, and in fact the reflectivities are a little less along those ridge lines. Now let's watch that storm make progress here as it begins to move eastward. We can also see that there's just so much convergence in this area that we've actually set up a very clear boundary on the radar. The radar's fairly close here, so we can see it. There's the radar right here, and we can see that low-level convergence boundary is set up. Watch this small cell here that moves into the Snake River Valley. As we go through time, you see that it dissipates as it gets into the colder air. A little lightning discharge here as the grapple falls out, and then it goes away. Meanwhile, our right-moving storm down in the valley here doesn't really get going until it encounters some of that rich air that's associated with the towering cumulus on those ridge lines, and it gets very large very quickly. Takes on sort of an HP look to it, although it's not really an HP, but it doesn't really have any good circulation signatures. There's no mesocyclone at this point or anything on the radar. As we go along here, we come down into the valley, and as it comes down into the valley, we begin to develop a small inflow notch here. Two reasons for that. Number one, a little less moisture. The updraft weakens ever so slightly, but there's a lot stronger flow down these valleys with southerly flow. Got some nice channeled strong winds right into the updraft there. See, there's still lightning being produced for this time of year. That's amazing in that region. We now go up to the next ridge line, and we find, again, the updraft gets enriched with a lot of preconditioned air. Then we get down into the valley, and we begin to develop sort of an inflow notch right here. This is a fairly wide valley, and that was able to maintain a pretty good influx of very strong southerly flow all the way from about this time here, which is 2241, all the way up into about 2315, and then it gets up on the next ridge line and sort of takes on a bigger and more of a heavy precip signature. Right about the time that it was in this valley, right here, wasn't a big tornado, but there was a tornado that formed, and I'll show that next. And this is a tornado that formed in the valley there south of Pocatello. This was from a series of pictures. It stayed in contact with the ground here about 10-15 minutes or so. Of course, you can see there's nothing to damage, but even so, it was clocked as it was recorded as an F1, mostly an F0, but there was some spotty F1 damage within it. Not a very big deal, but it's April, and it's up at 5,000 feet, and it's in Idaho, so that's pretty unexpected and pretty interesting as far as I'm concerned. Last, what we're going to look at here is one of the things we've been urging the AWIPS people to do is allow the forecast office to not only see the satellite data as it's remapped into AWIPS, which is a necessity, but also maybe let the offices, when they're in RSO mode, see the unremapped data taken at the satellite angle. And here's one good example of why you'd want to do that. This is the goes east. This is going to be a goes east loop, and it runs basically from about 14:15Z to 01:31, so it's mid-morning to late afternoon, right through the tornado time. And what we're doing is we're looking at these storms from the southeast at a really, really stark angle. The satellite is sitting at 70 degrees east, which is over the South Atlantic, right over the equator. And as we go through time here, you can see the great angle that you get on the storm. Now, this is RSO. Nobody put the goes west satellite into rapid scan on this particular day, but the GOES East was put into rapid scan for another reason. But imagine if you could be in your forecast office and be able to see both satellites anytime you wanted it, and be able to see them either remapped or not remapped. Take a look at this storm as it forms and gets traveling along here on this boundary, right in this region here, right there. Let me move that out of the way now. Now just watch this storm, right? This guy right here. You can see the crisp anvil, but you get kind of a chaser's eye view of the thing, because now you can look up underneath it and you can see the flanking line. You can see the towers in the flanking line, and you can see that the flanking line and the updraft of that storm are actually connected to that convergence boundary that we've been looking at on satellite and on surface obs. So let's move forward a little bit in time, and we can now see those inflow feeder towers as they form. This is just about the time that the storm is becoming its most intense, and we can clearly see the flanking line back at this time, and the inflow feeder towers there very, very clearly. And as we get later and later in the day, you can see that overshooting top pulse up and down, and the flanking line form and go away. Now I'm going to run this loop a little bit, point out a number of things. You can see the shortwave is still kind of having trouble making it out of the Boise area. It finally sort of weakens as it gets up into the diffluence. This new shortwave comes along, triggers stuff here, here, and here, and we have that nice little right-moving storm. Very, very nice view. Very, very good way to view a thunderstorm is in the unremapped GOES East data when you're out around 110 west, or further west even than that. So in conclusion for this case, use satellite data, identify those short waves, especially when you've got a good strong jet in the area and the circulations and shears are getting mixed together and making the 500 millibar vorticity analysis look a little like a plate of spaghetti. You can use the satellite imagery, help straighten some of that out. Watch that morning cumulus again form. Kind of confirm areas that seem to be convergent on the surface data, on the surface analysis. Are developing clouds. If they are, that means that's a pretty significant boundary, just like in the case of 10 November the other day. Case of 10 November that we look at a little later, we'll see that there's that one of the things we want to look at is persistent cumulus lines to identify areas that have a particularly ominous threat in terms of convective development. In this case, this line of cumulus along the northern edge of the ridges was there most of the afternoon, and it was clearly going to be where the most severe activity was going to occur if it did occur. And when that storm started moving down that line, it's kind of a no-brainer as to which storm was going to be the nastiest. Storm scale, remember, look for those signs like flanking lines, cumulus inflow feeder towers, and towers on the backside of the rear flank downdraft if one develops. All of those are signs that the storm is going to get it is severe and probably will remain severe for a while.
Our next case is from 10 November 2002, and this was a pretty significant tornado event. There were more than 90 tornadoes with this particular event over a pretty big area. So in order to simplify things, we'll break this down into various sectors. I'll deal with the northern sector here first, which deals with Ohio and Indiana, and then a little bit later on, John will deal with the southern states down here. Let's open up with the water vapor imagery with the 500 millibar heights from the Eta overlaid, and this goes from the overnight hours to the early morning hours. Pretty significant trough over the northern plains moving towards the east, and we can see some areas of convection here over Indiana and Ohio moving off to the northeast, and we'll look a little bit later to see if that plays any role in terms of leaving a stable air mass or not. Here's the Eta with the MSLP as well as the surface winds and Cape, which is shaded here. Pretty strong low over the western Great Lakes at this time. Let's advance to the 6-hour forecast. And the low is moving slowly to the east with a cold front extending something like that. Dew points were pretty high ahead of this front into the 60s, pretty far to the north for this time of year. So the Cape was appreciable here east of this front. One thing to keep in mind is this area here in Ohio and Indiana. The potential reason here for some lower CAPE values is because the Eta did have quite a bit of convective precip over Ohio and Indiana. Further south, though, we do see quite a bit of CAPE developing, and by 0Z, here in the 12-hour forecast, we can see CAPE values 2,500 or more across Mississippi, Alabama, and Georgia. And again, John will be talking about that region a little bit later on. Here, let's go to the visible satellite imagery, and we can see a few interesting features here. First of all, here's that area of convection moving off toward the northeast from West Virginia, moving off towards the northeast. When we first looked at this, we thought maybe this was a cold front, I should say a warm front, moving to the north here, but surface observations showed that that was not the case. We see a couple other interesting features here, one moving across Kentucky towards the east, and then another one right behind that moving towards the east. And when you first look at that, you may think of it as a boundary, but in this particular case, you can see this feature here as it moves towards the east. It's actually going over the top of some of the low-level clouds. So this is likely some sort of wave generated by the strong flow aloft, the jet, and just propagating towards the east here. Now compare that to the feature that's a little bit further west. What I'll do is stop the loop and advance it to right here. Here's that line I was just talking about, and here's the one that's a little bit further west of that, oriented something like that, with better vertical development on the cumulus here. And then most importantly, if we look at the orientation of the cumulus field, something like that east of that line, and then something like that southwest to northeast oriented west of that line. So we can infer convergence here. And remember, what we're looking at here is the integrated boundary layer flow. So at some low level here, we have convergence here in the low levels associated with that boundary. So quite a few interesting features there that we see in the loop. And what I want to do next is just turn up the loop speed and rock it back and forth. And the reason is there's usually a few other things you can see, because when you run it loop fast like this and have it rock back and forth, persistent features will catch the attention of your eyes much more quickly here. For example, look at this feature in extreme southeast Illinois. I'll just go ahead and draw it in here. It's moving off towards the northwest, and it's actually underneath some of those mid-level clouds over it. So something that's moving off towards the northwest here, and it seems like it may play a role in terms of initiating some storms here along that front right up here. There's another one up here in Indiana that's a little bit more subtle, but by turning up the loop speed here, we can generally see a few more features that you can't see in the more moderate or slower loop speeds. Next, let's go to the sounding. This is from Wilmington, Ohio, in southwest Ohio, and this is at 12Z. We can see, again, fairly good moisture here for November, so with some afternoon heating, we get CAPE profile. It looks something like that. So sufficient CAPE and good deep layer shear, and pretty good directional turning at low levels here, pretty strong winds. So SPC had their pretty large area of high risk and a moderate risk area over a pretty big area. So the question you always ask is, can I identify localized regions where the near storm environment is more favorable for some of the more intense storms? In other words, will one of the storms of the day be in my CWA? So we'll help answer that question by next going to the satellite loop and see if we can identify any features which may lead to a more favorable near storm environment. Okay, here's the visible satellite loop a little bit later on, and we overlaid the cloud-to-ground lightning data here to help you out in terms of identifying the squall line and any storms just ahead of the squall line here. Now, remember earlier we were looking at a couple features here. This first one here, which we said was most likely not a low-level convergence boundary, but something associated with a gravity wave, or generated by the strong flow aloft, the jet, and so forth. And this is not connected back to the squall line that we see here. However, that one a little bit further west, we concluded that this was a low-level convergence boundary because we saw the cumulus field oriented in different directions ahead of and behind that boundary here. And also, this is pretty important because it's connected back to the squall line here. If we follow this along something like this, that this is indeed connected back to the squall line. Then if we follow the portion of the squall line that's pretty much connected to that boundary here, I know there's some cirrus clouds in the way, and we'll look at radar next, but I want to focus on this storm right here. This is actually connected to this line right here, and it's also just ahead of the squall line right here. So this should be something that would raise a red flag. In other words, be very careful paying attention to this type of situation where you have a storm along a boundary here just ahead of the squall line. It has a much more favorable near-storm environment compared to storms throughout the region here. Okay, here's that radar data. Remember, there were some cirrus clouds leading up to where the boundary intersects that storm. So here we do indeed verify that it is connected back to this storm here. And what I'll do is stop the loop right here. And as this line went through this boundary here that we had been analyzing, the surface obs did not show a change in wind direction here. However, it may be just off the ground because remember the low-level cumulus that we saw was indeed oriented in different directions ahead of and behind it here. So that means the wind flow in the vicinity of this storm is something like this, where we have much better inflow into this particular storm just ahead of that squall line. So by following this feature here, this line that was pretty well organized and became deeper with heating during the day, connected back to the squall line, that's something that you should really focus on. And indeed, it did create for a much more favorable near-storm environment for this particular storm. And on a day where, like I said, there were more than 90 tornadoes, this was one of the most intense of the day here as it moved into Ohio. And right about there, it produced an F4 tornado. And again, something that you can anticipate here by following these type of features in the satellite data, radar data, and so forth.
Okay, now we're working a little further south, same day, 10 November 2002. We're going to be looking at the Nashville and Morristown, Tennessee CWAs, and the purpose of this very short segment is to learn to recognize and track mesoscale features that turn out to be important to convection later in the day, but maybe not be well handled by the model. Maybe they're too small to show up very well on the models. So to show you that the area in Tennessee is just as unstable as that further north, this is the 12Z sounding at Nashville, and it verifies the high cape and the reasonable shear. But again, the question is, where is the activity going to form? Is there anything we can find either in the analysis, which we couldn't, or the satellite imagery to help us kind of narrow down where we want to look for the development of severe weather? And in this case, there is. So what we'll be looking at now is a visible loop from early morning, 13:15, to late afternoon, 22:10 UTC. And we're going to be looking at the visible loop in an attempt to try to narrow down where we think the convective weather is going to occur. As we step through the loop here, in fact, let me just animate that and let it go one round here a little bit now. Stop it. As we animate it, remember we're working in the western two-thirds of Tennessee here. I think you can see this little feature right here moving into the area that really didn't show up very well on the model. In fact, no one here anyway noticed it on the model, and nobody down that we spoke with that were contributors to this session noticed it in the models either. If we go forward here a little bit, what we find is a little wave-like feature. Remember that this was mentioned in Dan's segment, this little line right here in Kentucky stretching down into western Tennessee. Then there's a little wavelet right here. And we went back and looked at the models. We did actually find the feature on the rock, on the 700 millibar analysis, we found a little wave there with a little bit of vorticity and whatnot, but didn't show up very clearly. It's nothing that would really catch your eye. It was kind of subscale to the model, but it shows up very clearly on the imagery. And if you are sitting here in western Tennessee, central Tennessee, wondering if and when things are going to occur, and you see a feature like this, coming along, then you can think of that as a focusing mechanism. Now, you can see here that indeed the deepest convection does form right at the cusp of that feature. Animate that and take this out of the way. Notice also that the cloud line that's associated with that wave is not really low-level cumulus, and you can sort of see that as the enhancement passes across the low-level cloud field. It's actually a 700 millibar feature. It shows up, as I say, it shows up a little bit on the ruck, and it's at that point where the strong storm, where the only strong storm of the day actually forms, or the only tornadic storm anyway, forms. You'll notice here that the cloud streets in Alabama at the beginning of the loop, again I'll stop it, near the beginning of the loop, look much more unstable. They're larger. Cumulus within the streets are much larger than they are in Tennessee. There are also more lines, more clear, more well-defined lines in Alabama. But as we walk through the loop here a little bit, you can see that with the approach of this little disturbance and also probably the southerly flow, we find this line of cumulus now moving into the Morristown CWA, and we do get a lot of enhanced cumulus just as the wave moves in. So something to pay attention to. And what I've done here is I've created a storm relative loop, if you will. I just follow this storm, the cusp, that little feature we've been watching kind of goes like this. And this is the storm that's at the cusp right here. And if you'll notice, as time goes on, you'll see that I just try to keep that storm very near the center to watch what's going on around it, and also just watch its history as time goes on. I've also overlaid the lightning data so that we can keep in mind some of the stuff we learned in Lightning Met 1 and 2 when we're looking at severe weather. So I'm going to start stepping through this, and you see the storm now moving a little bit north of Columbia with time. We've got, this is 5-minute lightning data, and we've got some positive. We've got a low count, but notice that at least in this updraft, the strikes are positive at this particular time. We go along here, and most of the strikes you see on here are with this storm, and we have a very high positive count. We have almost 50% of the strikes are positive at this time. Another sign that that's a severe storm. And going along here, as time goes on, you see that the number of strikes in a 5-minute period stay just about the same until we get up to about maybe this time here. Well, no, it's kind of pulsing throughout this period. Another sign, remember, that there may be something afoot. Pulsing updraft is a sign of a severe storm in many cases. We get up here to around 2200, and we begin to see the count jump up severely right in here. We've had some pulsing behavior, low counts, but now we have a fairly high count, a 5-minute count, and a lot of the strikes within the updraft are positive. This occurred just as a storm to the east in the warm sector passed east of our storm, but I don't think that there's a relationship, or we don't know if there's a relationship or not. I don't think there is. I think this storm is just traveling along with that cusp, and it's just getting stronger with time, and you can see here that's reflected both in the reflectivity pattern and as well as the total lightning CG count. So as we go along here now, 2218, we get a first tornado touchdown, and the storm is definitely positively strike dominated at this time. We go to 2230 here, and some wind damage is reported, but I believe it was tornadic. We have hail going on throughout this whole thing, some fairly large hail, up to 2-inch diameter hail. Again, pointing out the lesson that we taught in Lightning Meteorology 1 and 2, that especially Lightning Meteorology 2, that even though positively strike-dominated storms are more common on the plains, anywhere you find a storm, in a severe storm environment, when you find a storm that has a lot of positive strikes in the updraft of the storm and a very high total positive flash count, that is a storm to be aware of. And indeed, this particular storm produced several tornadoes throughout this next part of the loop here, and it killed 2 people. It killed 2 people right about this time here. So it was a very dangerous storm, and it was positively strike-dominated throughout most of its life. There was pulsing behavior early on. And as we get toward the end of the loop here, I'd like you to look at the radar in the following sense. Remember what we see on satellites sometimes. We see those inflow feeder clouds. Well, here we are approaching the radar. We get a lot closer to the radar. We see some strikes out in here, and we don't know what that's from, but as we get closer and closer to the radar, we now begin to see some of these inflow feeder clouds that are associated with the towers we're seeing on satellite. So there is some deeper cumulus developing out here, but not quite deep enough to be within the confines of the 0.5 degree tilt when the storm is fairly far away from the radar. Okay, that was sort of an aside discussion of how to use satellite to identify small-scale features that maybe aren't identified by the models. I'm sure we're all used to looking at satellite enough to recognize things like that, little wave-like features or apparent boundary features to focus activity when the activity is expected. What we're going to do now is we're going to slip into the southeast U.S. and we're going to learn to use satellite data to not only identify short waves but also learn a little bit about their intensity, and then we're going to finish off with some terrain discussion, believe it or not, in the state of Georgia. So here we have the a water vapor loop which runs from 1900 on November 10th to 23:15 most of the afternoon over the southeastern U.S. And what we're looking for is a short wave coming in for the evening hours, and there's plenty of clues that that's coming in. Let me just walk through the loop and show you what those clues are. It's kind of a weaker shortwave. It's a not quite as clear a shortwave to spot as maybe this early one was, but one of the things you want to look at when you're expecting an evening shortwave, which we were at this time, notice along the jet cirrus here that's associated with this big trough, we find a little distortion, like it might be the beginning of a cusp or a baroclinic leaf, like we've talked about in cyclogenesis. This is indeed a very small-scale baroclinic leaf, and it's associated with that shortwave. It's distorting the dry side of the jet. And if you look down here on the south side of this feature, down around here, you'll see there's a little dry slot that's coming in just south of it. This is a little more subtle maybe than the more intense shortwaves you're used to seeing, but if you're looking for a shortwave, these are some of the things that you're looking for. The little hint of a mesoscale baroclinic leaf and a little bit of a dry slot to identify that shortwave. Right toward the end of the loop, of course, we see some, we're simulating working in the Jackson, Mississippi CWA, and right at the end of the loop we see some convection being triggered right ahead of that shortwave, confirming that it is a fairly intense and significant shortwave. So let me run this loop a little bit. In fact, maybe I'll run it just a little bit faster and try to let you see how that wave appears as it travels through northeastern Oklahoma there and into Missouri. Now, one of the things you might not have thought about using, but it's possible to use to kind of get a handle on how intense the shortwave is and where it is. This is the 3.9 micron infrared channel from 2000 to about 0Z, 2045 to 0015. Near and especially after sunset, we advise looking at the 3.9 micron imagery for several reasons. 3.9 micron is better than 10.7 in terms of delivering information about cloud fields, since the 3.9 channel can be used to discriminate water clouds versus ice clouds. In this particular enhancement, let me stop this at the beginning. In this particular enhancement, the cirrus clouds, or rather the cold thunderstorm tops, are noisy because it's outside of the range of the 3.9 channel. The black clouds here are basically ice, and the lighter gray clouds are water or water-ice mix. When the darker that the gray gets, the better the chances are that we're looking at water-ice mix. As we start moving along here, as the shortwave begins to move toward our area and we're expecting it, we see this area of sort of medium gray clouds moving into western Mississippi, right ahead of that shortwave. Just as these thunderstorms are developing up in here, let me step forward one more time. Right at this time, Jackson is reporting ACUS. So what we're looking at, and when you look at the 10.7 micron channel and use that temperature to compare with the Jackson sounding, nearby soundings, proximity soundings, we find out that these clouds are around 12 to 14,000 feet. They're being reported as ACUS, and watch as the shortwave comes in how the altocumulus field begins to get very, very dense, and then as the storm lines form, you'll see them dissipate in response to the compensating subsidence associated with those very strong thunderstorms. A lot of times that's a very good clue as to how strong the shortwave is, or how strong the squall line is. These tops come up very, very rapidly. There's compensating substance between the two lines. The ACUS the ACUS dissipates very, very quickly. Let me just animate that and let you watch this. The ACUS dissipates very, very quickly as the storms go up. Another indication that we're looking at some very strong thunderstorms here. And you notice out here in the warm sector over Alabama and Georgia, we've got some low-level cloudiness that's flowing up into the region ahead of this approaching squall line. This is a series of soundings from the day, from this day, 10th of November, taken at Jackson, Mississippi. This is the morning sounding here, showing a very strong cap at that time, fairly unstable air mass though, with some pretty good winds aloft. And as we go through time, you can see that low-level inversion begin to lift out. And finally, when we get to the late afternoon, you can see that the inversion is very, very high. This little glitch right here is probably an effect of the low-level ACUS that's formed around the time that the sounding was released. This is a pretty interesting demonstration of how topography can play a role, even in areas where you don't normally think about topography playing a role. What we're showing here in the background is topography, and we've overlaid surface observations on it. Notice the dew point gradient across central Alabama and also central Georgia. This corresponds to a region where terrain is increasing, and we spoke with forecasters both in Birmingham and in Atlanta, and this is a fairly common thing. We have dew points a couple, 3, maybe even 4 degrees higher down here in the southern portions of these states, and slightly lower dew points up here, even though the relative humidity might be a little higher. Because of the terrain, the dew points are climatologically a little bit less up in here. Now what I'm going to do now is I'm going to fade this loop. I'm going to go from the terrain to the 3.9 micron imagery here, and we're going to slowly go between those two. And as we do, I want you to notice how in a lot of places the low-level cloudiness seemed to correspond to the terrain features. Notice up here in Georgia, got some low-level cloud lines. We've got southerly flow, a lot more low-level cloud lines here in southern Georgia. They're kind of having trouble getting up on that higher terrain. When they do, of course, it's going to be upslope, and it's going to be increasing relative humidity and all of the things we expect with upslope flow. But right here at first, you can see that we've got this image, by the way, is late afternoon, 2200. And now we see that the low-level moisture hasn't pushed up onto this plateau yet. Over here we can see almost a one-to-one correspondence between the low-level cloudiness and the terrain. And so even if you've got terrain features which are very, very small and very insignificant, they may actually be playing a role in your weather, and if you're not aware of them already, you should become aware. So let's look at a little bit of reflectivity data on those storms that went up over in Mississippi. Now the storm lines are up, and the eastern line is ready to move into western Alabama, and as you can see, and as expected, those storms get very intense very, very quickly. The first storm to cross into Alabama develops a hook and produces a tornado about 0045 just as it crosses into the state, right about here. Produces a fairly large tornado right in there, so no big surprises. The next storm coming into view in eastern Mississippi produces an F3 tornado right in here. So this is a very tornadic squall line at this point, and I'm going to animate this loop just a little longer to show that as time goes on, these lines begin to, these cluster of storms begin to line out into a squall line configuration. Meanwhile, here's another squall line. Here's that second squall line kind of catching up to the first, and everything looks like it's going to be lining out. Again, just a reminder of the use of lightning data here. Be sure to always look at the lightning data. I've done another one of my famous storm relative loops. I followed the storm. It's produced artificially, but it lets us track the lightning and be aware that of lightning behavior as we go on. We're looking at velocity here, and as we go through time, you can see that the storm begins to intensify considerably. Here's the strike count for this area right up in here, and notice as we begin to develop a shear, the lightning count, total lightning count, goes up appreciably, but the positive counts go up very, very high, and a lot of those positive counts are there where that biggest shear is, which is always a good sign for severe weather. So again, make sure to use that lightning data when you can. Just a reminder. Okay, so now let's look at the GOES 10.7 micron IR loop from 01 through 10:30 the next morning. The loop basically shows the activity that appeared to be lining out as it moves east. But what I'd like you to notice is that as the squall line continues to develop, there are definite signs of individual tops embedded in this line, even though the radar, the low-level reflectivity field, looks pretty much linear, and we'll show that in a minute. There are definitely tops within this line that are getting up much higher than most of the other activity in the line. So we've got some isolated cells in the line that have much higher cloud tops. This one in particular looks really good as the storm is crossing from Alabama into Georgia. Now, another thing to notice on this particular loop is that we've got a little feature here in northeastern Georgia, and I'm going to animate the loop. And what that feature is that's that cooler terrain, in this case along the southern end of the Appalachians, upon which clouds are developing. But even when they're not developing, you can still see signs of the terrain there. What a lot of people don't realize, who don't work with terrain all the time like people in the western regions do, is that several things happen when you're dealing with upslope flow. Not only do you have, in this case, southerly flow moving up on the higher terrain and the relative humidity is increasing, but also if you look right here, you'll see a band of light brightness, which is associated with a small cloud field developing along the southern edge of the Appalachians as that moist air begins to pile up or dam up against the southern end of the Appalachians. And a lot of times when you've got terrain in your area and the flow is just right, you'll find the boundary layer deepens right along the upwind edge of that terrain barrier, and that is a very, very nice preconditioned air mass. And here at night, it shows itself very clearly. If you're looking for it, shows itself very clearly as an enhanced area, even on the IR. With this squall line approaching, you want to pay particular attention to that area because it seems persistent. Anything that seems persistent, even if it's on the very poor resolution, well, not very poor, but 4x2 kilometer resolution IR data that we currently have, and in the future, again, we'll have twice as good a resolution, so it'll be much clearer to see, much easier to see these things. You definitely want to pay attention to storms that are approaching that area. Now we're kind of zoomed in on northeastern Georgia. Here's the southern edge of the Appalachians at this point. We've got that southerly flow coming up into here. The IR data showed us that right in this area, right along in here, we were developing either a cumulus field or a deeper moisture field that was showing up on the IR as being just a little bit brighter, right where we'd expect it to be if there was going to be a preconditioned air mass due to that cold air damming. That moist air damming in this case, unstable air. So now let's look at this squall line approaching from the west. Here's the squall line. You can see that there are some isolated storms within the line. What I'm going to outline right here now is I'm going to put the 1,200-foot contour line associated with that southern terrain feature right here. This is approximately, let me change colors, and this is approximately where that feature appeared on the infrared that indicated maybe some low-level cumulus developing there. You can even see some pretty good reflectivity moving up into that terrain. But watch these storms as they move up into that area that's been preconditioned by the upslope flow. And again, we're in Georgia, where one doesn't normally think of upslope flow playing a big role, probably Atlanta does, but not too many other people. Watch these three counties right in here, and you'll see that storm intensify appreciably as it moves along into that preconditioned air. And indeed, there are several tornadoes that occur, including an F2 tornado at, let me go back to when the F2 tornado is, which is right here. There's an F2 tornado as the storm moves up onto the terrain. And here there is and at this time right here, two people are killed by a tornado pretty much in the middle of the night. Let's toggle on some lightning data and show you how that lightning behavior changed as the storm moved up onto the terrain. We find a lot of lightning with the squall line as it moves eastward. Some of these cores look pretty active, so they are severe, and indeed they are producing hail. But as we move up onto the terrain in this storm, watch the strike count, especially the positive strike count, go up with that particular storm. Very interesting 5-minute lightning data. Very high strike count right with this storm right here. A lot of them being positive, and just yet another sign that we're dealing with severe weather. But the nature of the terrain, our knowledge of kinematics and thermodynamics helps us understand why that storm got so much more severe than a lot of the others in this line did. Here's some low-level velocity data showing that same area as the storm moves up onto the terrain. Fairly decent velocity shear signature develops up in there. I'll toggle on some lightning data to show you the area we're looking at right in there. Toggle that back off. So again, pretty much the only storm that's got a fairly decent shear signature, and the only one that's producing a tornado, in fact a killer tornado at this time. So in summary, for the whole November 10th case, from Dan's segment over Ohio and Indiana, remember we want to spend a lot of time looking for persistent convective cloud bands that seem to deepen with time. Those are going to be big role players in the near storm environment. Enhanced cumulus areas, we want to look for them. We did back in the New York, in the Pittsburgh and in the eastern Pennsylvania case. We looked for those areas of enhanced cumulus. In the Tennessee case, we saw that little mesolow move into western Tennessee, and the cumulus enhance in front of it as the feature moved across the state. Mississippi and Alabama case, 6.7 micron imagery can even help us find very subtle short waves if we look for signs like, for example, we look at in cyclogenesis, we look for maybe the beginning of a little distortion on the jet side, on the shear side of the jet, which might mean kind of a baroclinic leaf or a miniature mesoscale baroclinic leaf trying to develop a little bit of dry air coming into the south. And using the 3.9 micron imagery, we were able to answer some questions about how the near storm environment was responding to the thunderstorms, in the sense that the ACUS field dissipated as those storms went up. And once again, the terrain in Georgia was shown to be important for that tornadic storm in the middle of the night. Occurs in an area where you've got upslope and deepened boundary layer on the south side of the Appalachian, so it doesn't just happen in the west, it happens anywhere where there's terrain.
Our next case study is from 20 March 1998, and for this one, we'll pretend like we're forecasting for Blacksburg and Raleigh. Here's a water vapor loop for this case here, and we can see a closed low here, upper low over Tennessee, with various short waves rotating around the trough. We can also see a dry slot moving towards our region here in North Carolina, which may play a role in terms of destabilization. Now, if I speed up this loop, notice this short wave that we can track from Louisiana across southern Mississippi, Alabama, and into Georgia, and moving up in this direction here, and it would come into our CWA by later in the day. Here's the 500 millibar heights and the winds from the Eta. This is at 12Z. Here's that upper low, and we could see pretty good diffluence as well as strong flow over our region. If we go to the 6-hour forecast, height falls occurring as well as pretty strong winds, 50 to 55 knots here at 500 millibars. Here's the sounding from Greensboro, North Carolina at 12Z. And remember, this is March, so this moisture is actually pretty good with if there's sufficient heating. And with the forecast heating, we can see CAPE values running something like that. So sufficient CAPE, good deep layer shear, and good directional shear here, as well as pretty strong wind speeds. Another thing to note is the inversion here is relatively weak, so storms will go up fairly early. Here's the ADA forecast CAPE. It's shaded here. The 3-kilometer storm relative felicity in the yellow contours here, and then the 6-kilometer mean wind barbs here shown as well to give you a rough idea of the storm motion. Let's go to the 6-hour forecast valid at 18Z. We can see quite a bit of CAPE developing here in South Carolina, into southern North Carolina, but not as much into central and northern North Carolina, into Virginia. And what I did here also was plot the convective precip from the ADA, and we do see quite a bit of convective precip forecast for that area, which can be holding back the CAPE forecast for that region. We do see pretty good shear values here, around 200 for the helicity value, and storm motion being approximately north-northeast at this time. Go on to 0Z, again, a lot of shear, and the instability still doesn't look that impressive, probably because we have some convective precip here from the ADA. So that's one of the things we'll need to monitor as we go through the day, is how much destabilization will take place. Now, to help us answer the question about destabilization here, first thing we'll look at is some surface observations, and I'll slowly advance through from the morning hours to the midday hours. And I'll go ahead and stop it at this particular time, 18Z, and just analyze our warm sector here as running something like that with the warm sector in here. And also note the winds here back in the drier air being pretty strong out of the southwest, which would infer a pretty good convergence along this portion of the front right here, where we have pretty good southeasterlies in this region in North Carolina. Dew points are fairly high, and temperatures are starting to warm up, low 70s down here at Charlotte, and mid-60s here in North Carolina. Remember to keep in mind the storm motion here as well, being towards the northeast. That means any storm that goes up along the warm front over here will move quickly into the stable air, become elevated, and not live for very long, or at least to have a chance at being severe for very long. However, over here on this portion of the line, any storm that goes up here will have a longer residence time in the warm sector, and therefore give it a chance to intensify and become more severe with time before it finally hits the warm front up here. So it looks like the greatest threat area here would be along this portion of the front here, where we have the greatest convergence, the strong southwest winds and the strong southeast winds here along the front, as well as a longer residence time in the warm sector. Here's the visible satellite imagery for the morning period through 1815 UTC. And remember, the ADA had quite a bit of convective precip over this area, leading to lesser CAPE values. Well, what's going on here in reality is we're not only not seeing that precipitation taking place here in terms of widespread convective precip, but also we see some breaks in the clouds actually through North Carolina. And that's leading to higher temperatures and, of course, much greater CAPE forecasts than what we saw in the ADA, just ahead of that front. So more CAPE than what we expected, and we see storms already developing along that portion of the front. And by the end of this loop here, you can actually see, I'll stop it right here, kind of a bulge in that front, something like that. Remember, we had pretty strong southwest winds along this portion of the line and strong southeast winds. So again, pretty good for convergence along this portion of the front. And remember, that is the area where we expected the highest threat in terms of the storms having a longer residence time in the warm sector as they travel off towards the north-northeast here. Next, we have the visible satellite imagery for a little bit later on, and here we see various lines of convection going up in North Carolina and South Carolina. And remember the area we were most concerned about was the northwest portion of that line in the state of North Carolina here, and we can see the various storms going up in that vicinity. What I'll do is go ahead and stop the loop at, say, this time right here, and I'll go ahead and tell you that one of these two storms here was tornadic. This one right here is shrouded by anvil from the southern storm down here, and that southern storm right here has some anvil from another storm further south. So in terms of some storm scale features like we were talking about earlier, difficult to discern. We have some anvil in the way here. So I will go to radar here soon and kind of show the answer, but let's first look at some more satellite data as well as some reflectivity data here to analyze this situation a little bit better. Here's the reflectivity from the Blacksburg, Virginia radar here, and what I'll do is stop it at the time we were just looking at in the visible satellite loop, and that's just about this time right here. Here's the northern storm I had pointed out, and here's the southern storm I had pointed out. Now both of them look pretty similar here in terms of reflectivity structure, but let's again look at some more data here to see if we can get an additional clue about which storm here is more severe. Now let's look at the 10.7 micron IR imagery here, and again I'll stop this loop at the time of interest, and here's the northern storm we had been looking at. It has an enhanced V signature as well as colder cloud tops, and here's the southern storm right here, which does not have an enhanced V structure, and also the cloud tops are actually warmer. So that additional piece of information, this clue here would say that this storm right here is most likely the more intense one. Now next I'll show the velocity data here and give us the answer. Here's pretty much the answer to our question here as to which one of these storms is more severe or more intense. This one right here has a pretty good couplet. This one had an F3 tornado associated with it, and this one right here just had some hail reports associated with it. And the reason I wanted to show this is to emphasize the importance of using RSO if you wanted to get an additional piece of information about the storm. In this particular case, we used an example where we're pretty close to the radar, and we can see this pretty good change here in terms of the velocity signature being a lot better for this storm right here. However, imagine a scenario where the storm or storms are far from the radar, and we're looking too far up in into the storm to really get a good idea in terms of how intense that storm is. Or imagine if the radar is down, and you need to get an additional piece of information about that storm. Of course, we could use lightning data like we were talking about earlier, but in this particular example here, we used RSO satellite imagery to help us give us an additional piece of information about the storm. And remember, we can only do this if we're in RSL mode. If we're just in the regular 15-minute schedule, we don't get the data on our AWIPs fast enough to enable us to make these decisions on a fast enough time period here. So this is, again, emphasizing the point, whenever you think you're going to get some convection, or whenever you see a need to use RSO, go ahead and call it. If you need to use it, it's there for you. Now, conclusions for this case. On the synoptic scale, we saw a dry slot approaching the area, which led to some partial clearing and destabilization. Important shortwave rotating around the base of the trough, which later played a role in terms of initiating and intensifying the convection. On the mesoscale, we saw air mass destabilization, as well as a dry push towards some of the more intense storms, and convective bands in the warm sector. On the storm scale, we saw some colder cloud tops and an enhanced V with some of the more intense storms. And the main point there is that you can use RSO data to get additional piece of information about the storm, especially when the storm is pretty far from the radar and you're looking just for an additional clue about that storm.
My name is Dan Lindsay. I'll be taking the quiz portion of this, and since this is an audio session, we won't be able to actually quiz you directly, so I'll basically just go through this as if it's a case study. The first day we're going to look at is 4 May 2003. This was the beginning of about a week-long severe weather outbreak in the Central Plains. On this particular day, the severe weather was limited to eastern Kansas, eastern Oklahoma, Missouri, and Arkansas, as well as points further east. What we're looking at here is a visible image around 19Z at 4 May 2003 with the surface observations overlaid, and there's several interesting features which we normally ask the students to point out. The first is simply a surface low-pressure area located in this region with a dry line, which is evident both in the cloud line and the surface dew point observations extending in this region. I've drawn it sort of as a warm front, but this is actually a dry line. There's also this secondary convergence line, which is evident east of that, which I'll also draw in red, something like this. And you can tell that it's a convergence line both by the fact that there's towering cumulus on the northern end and by the fact that we do have converging winds. Notice the southeast winds here in Kansas City, the southwesterly here in Emporia, Kansas. And additionally, there is a bit of a dew point gradient, about a 10-degree dew point gradient across this line. The actual warm front on this day was probably located something like this, being hindered by the low clouds, but it did lift a little bit further north later on in the day. And finally, there is a cold front back here to the west, and you can see that by the northwesterly winds behind it. So as a forecaster on this day, you're going to want to be monitoring these convergence lines at the surface where we do already have towering cumulus going up here in northeastern Kansas. We also want to watch for development along the dry line itself. This is a visible loop beginning at around 19Z, which is where the last image on the previous slide was from. And you can see we have explosive convective development along that eastern line, the original convergence line, as well as on the true dry line back to the west. Notice there's lots of things to notice on this. I'm going to point out a few storms in particular. I'll start by stopping the loop and then going forward to about 2130Z, and the first thing you'll notice is down here in southeastern Oklahoma we have a storm which is formed and then split, and the storm which I'm pointing out here is a left mover. It's moving off to the northeast in this direction. And then the other interesting storm is this one here in northeastern Oklahoma, which actually formed on the true dry line and is now moving to the east. As we step forward, let me erase my annotations. As we step forward, notice the right mover. Now, it's starting to take on some of those supercellular characteristics which John and Dan have been talking about. That includes the overshooting top, which is evident here. There's a flanking line back this way, and some of those inflow feeder towers, which you can see here. And also notice the air out ahead of it in extreme southwestern Missouri has some cloud streets, and this is another sign that there's extremely unstable air in this area. I'll erase that and step forward. Notice the left mover now actually merges with, or at least intersects, or it's beginning to intersect with the right mover here at 23Z, and I'm going to talk a little bit more about that on the next radar loop. Other interesting features is the fact that if we go back here to about 2025Z or 2015Z, notice that the orientation of the left mover in this case is like this, while the right movers are more like this. And the reason for this is not the fact that we have diverging winds at anvil level. In fact, the anvil level winds were fairly uniform throughout this area out of the southwest. The reason is because the anvil orientation is actually a function of the storm motion itself as well as the anvil level winds. In particular, it's the vector difference between the anvil level winds and the storm motion. And for that reason, just because the left mover is moving to the northeast at 70 knots, the right mover to the east-northeast at about 40 knots, we have this significant difference in the orientations between the anvils of the left movers and the right movers. Here's the radar loop which I promised you from Springfield, Missouri, here in southwestern Missouri. And I'll let you look at it a couple of times first and increase the animation speed. The first thing which probably sticks out in your, is this left mover, which comes screaming up from the northeast into southwestern Missouri and then intersects that right mover. Let me erase that, stop the loop, and go forward to about this time, or maybe a little bit later, right at 23Z. At this time, the right mover, which is indicated here, has a really good inflow notch. It has a hook-shaped appendage, and it was producing a tornado here in Ottawa County, Oklahoma. The left mover is producing no tornadoes, but due to its rapid motion, it is producing some straight-line wind damage as well as some very large hail. As we step forward, notice the intersection occurs. It intersects the forward flank of the right mover, and suddenly the inflow notch goes away, which indicates that the updraft is weakened. Some of the precipitation has fallen into that notch, and it turns out that the tornado actually lifted during this time. And as we step forward in time, the right mover is able to reorganize and ends up producing a large tornado in Pierce City, Missouri, which hits the town directly and does significant damage. So in this particular case, the intersection or the merger didn't necessarily help out the right mover. It appeared to actually, it was more of a destructive interference, but the right mover was able to organize itself and form severe weather down the road. Now we're going to look 2 days later on May 6, 2003, and we'll start off by looking at some ADA analysis from the night before. This is the analysis at 0Z on 6 May 2003. What's plotted here, we have surface sea level pressure is contoured, the wind barbs are surface winds, and the colors are the surface dew point values. And you can see we have low pressure back here in West Texas with southerly flow out here in the warm sector, and we have the dew point, the highest dew point values are mostly in Arkansas and extreme eastern Oklahoma. And as we go to the 6-hour forecast valid at 6Z, you can see the surface low has now progressed to the Amarillo area. Going to the analysis at 12Z, the surface low is now in central Oklahoma with southeasterly winds throughout the warm sector. And then the ADA 6-hour forecast valid at 18Z takes these highest dew point values and advects them up to the north and to the west into southeastern Kansas. So as a forecaster on this particular day, you're going to want to track the advection of this moisture and see what effect it may have on the convection in northwestern Kansas, or I'm sorry, in eastern Kansas. And notice that in northwestern Kansas, a cold front, according to the ADA, is supposed to move through and bring some cooler northerly winds. This is a visible loop starting at about the time the sun comes up on 6 May and going to about midday or so. And there's several interesting things to note. First of all, notice the convection ongoing in western Kansas. And remember from before that the ADA was showing a cooler air mass in this place. If we turn on the METARs, you can see that northerly winds, temperatures in the 40s and 50s. So this convection in western Kansas is definitely elevated convection. It's rooted above the boundary layer. And even though it may be producing some severe weather, it's not something we should be too concerned about. The more interesting thing is to use the visible satellite combined with the surface obs and look for that return of moisture which the ADA was talking about. And we can do that by stopping the loop, going forward to about the time the sun comes up here at about 13Z. Notice the stations here in extreme southern Kansas and the station here at Ponca City, Oklahoma. Watch the dew point values as we step forward in time all of a sudden surge up. Ponca City has increased to 67, the station in Kansas to 59. And if you back up and watch, this is actually associated with this low-level cloud feature moving through, and I'll draw that here, the leading edge of it. So it turns out that this low-level stratiform cloud feature is allowing us to track, using the visible satellite, the low-level moisture return. And if we watch that moving to the north, it actually intersects this elevated storm on the west side of Emporia, Kansas, right about this time, right around 15Z, so this is still well in the morning hours. And at that time, the storm west of Emporia slows down, turns to the right, and actually ends up producing a tornado just on the western side of Emporia about the time that intersection occurred. And it definitely went from being an elevated storm to a surface-based storm. So in this case, we were able to combine the use of the visible satellite and the surface observations and track the low-level moisture return, and it ended up having a big effect on the ongoing elevated convection. Here's the visible loop which begins about the time that storm was affecting Emporia, Kansas, and goes out throughout the afternoon hours. And you can see that we once again here on 6 May have explosive convective development in eastern Kansas and most of Missouri. I'll increase the animation speed so you can see that a little bit better. Lots of things to point out on this loop, but I'll only point out a few. One is, notice the outflow boundary, which forms along the original convection and then tracks to the south. And as it tracks down, it actually allows the initiation to occur in a southwest to northeast oriented line. And these are probably the strongest storms of the day. You can increase the animation speed some more and even rock it to see that outflow boundary a little bit better. I'll let this go for just a minute so you can take a look at that outflow. Another very interesting thing on this loop, if we stop the loop and go to about 20Z, notice we have the storm forming here on the southwestern side of that line. Let's step forward and watch the evolution of that storm. There's a little bit of cirrus overhead, but you can definitely see here around 2115 suddenly the emergence of a flanking line, definitely an overshooting top, and some of those inflow feeder clouds within the warm sector. And this was a very dangerous storm. This was the so-called tail end Charlie forming on the southwestern end of the line. and ended up producing a tornado and quite a bit of severe weather. And this was certainly not the only severe storm on this particular day. There were quite a few others, but this is the one that I just chose to talk about. Here's the radar loop from Springfield showing these storms as they move into the Missouri, central Missouri, southwestern Missouri area. There's a very evident outflow which is associated with the original storm, which is moving in this direction, and you can track the outflow. If I stop this, go forward, the outflow boundary is very evident on radar, something like that, moving to the southeast with the storm. And it's interesting that the storm back here, which is definitely severe as it crosses into Missouri, gets into some of the more stable air behind the boundary and weakens with time. But the storm which forms down here in this portion to the northwest of Springfield actually latches onto the boundary. And we can see that happening right about here. Here's the storm, which is just now developing. And it actually tracks along the boundary, still able to ingest the most unstable air to from the south and from the east. And it also uses the vorticity from the boundary itself and is able to, I'm pretty sure, produce a pretty good tornado as well. So now I'm going to turn it back over to John Weaver, and he's going to look at one last satellite loop on this particular day.
Okay, well, here we are back at the same slide that we opened this session with, and that is the identification of different air masses. Hopefully over the last couple of hours you've learned enough to see just a little bit more in this imagery than you did when you first began. Of course, we can still see the warm sector here over Nebraska and western Iowa, and we can still see the stratoQ, or the stratus here over western Nebraska and western South Dakota. We can see this. We see these stable wave clouds up here where an MCS had traveled earlier in the day, leaving behind a boundary. Actually, this was a warm front that was sort of modified by that MCS traveling to the north of it, kind of pushed it back to the south a little bit. But as we animate this loop, or we go forward in time with this loop, I'd like you to pay attention to some of the features that we talked about as this course evolved. For example, in the warm sector, we'll be looking for persistent, deeper cumulus areas. And I think you can see in central Nebraska there, we have a persistent deep Q area right in here that needs particular attention as you go through this. As you go through the sequence. If you're in Sioux Falls forecasting, for example, and you see this boundary coming up into your CWA, and you see this area of enhanced Q, hopefully now you'll be looking for these interaction points and be looking for something to go up in the area where the instability seems to be the best, just by the behavior of the cumulus cloudiness in that sector. And you can see here that indeed right on that boundary enhanced cumulus line intersection, we do indeed have a thunderstorm that goes up. Notice that when these storms go up here to the south in northeastern Nebraska, we have a sudden clearing. This is probably due to blocking of the low-level flow by this storm, maybe due to that. Seems to be directly related to it, and indeed when this storm in South Dakota begins to entrain some of that more stable-looking air, the storm begins to show signs of dying, puts out a little outflow boundary right there, and pretty much dissipates quickly. Meanwhile, on the west side of the outflow that's coming up into South Dakota here, we still have some unstable air in this little area right here, and as we go through in time and this outflow moves back into that unstable air, we have a second round of convection that triggers, and a tornadic storm goes up right in here where the storm is now accessing some of this unstable air. This storm was the Manchester tornado, and for a brief period of time it did produce F4 damage in southeastern South Dakota. We animate this loop. There's a number of things you can see along the same line. We see this storm go up here near Omaha. North of it, we see some clearing as the storm stabilizes, as the outflow from the storm stabilizes the air mass, and that advects northward. We see a boundary here on the west side of the stable air mass, which goes up and intersects this storm. This storm intensifies and produces some fairly large hail. We see a little enhancement moving through western Iowa right here. As it intersects that boundary to the north, it triggers another tornadic storm. You can see the dry line right in here as the day progresses, and the differences between the two air masses are enhanced. We can clearly see where the dry line is. Let me stop that loop and go back and let's look at that a little more closely. We can see here roughly around 2100 or so. We can see a clear definition of the dry line. Cloud streets in the warm sector, very enhanced cumulus area here that we've already talked about, and very dry air back here in northeastern Colorado and southwestern Nebraska. And we can see storms go up on that dry line later in the period. So let's look at that. Let's look at that Manchester storm too as it gets going along here. Look for some of those signs that we've been talking about in terms of inflow feeder clouds, flanking line, overshooting top, above anvil cirrus, crisp anvil edges. Things like that should all be clues now, should all be things you look for when you're studying the near-storm environment in a severe storm situation. Okay, so that pretty much concludes the session.